So we were calculating transpiration rates based on basically what the primary driver for transpiration rates is the vapor pressure gradient. So the vapor pressure of the leaf, we did this at the very end of the last recording, so we're just going to repeat this, minus the vapor pressure of the air. And that's going to be the vapor pressure gradient. So that primarily is driving transpiration. But transpiration rates are inversely related to the degree of resistances. So in this case we're looking at the resistance of the leaf, which is the stomatal resistance, and the resistance of, plus the resistance of the air, which is the boundary layer resistance. So the vapor pressure gradient is ultimately affected by temperature and relative humidity, as we saw, as we will see in some calculations here. And the resistances, especially boundary layer resistance, is determined by environmental or climatic factors, and also by plant structural STR adaptations. Some morphology that are unique to limit to affect the boundary layer resistance. And then another factor that environmental factors here that we're talking about do include temperature and relative humidity. Temperature, relative humidity, but also wind speed, as we will see here shortly. But so again, looking back at our main calculation for transpiration rates, the vapor pressure gradient is the main influence on transpiration rates. So if you look back here at this diagram, you can see that basically over here on this side, where we're looking at a vapor pressure gradient, where inside the leaf it's high and outside of the leaf in the atmosphere vapor pressure is lower. So these are the boundary layer is going to influence that gradient. The how open the stomata are going to influence that gradient. Okay, so we're going to take a look now at climatic factors that affect transpiration rates, or environmental factors. So first we start with relative humidity. It seems to have the greatest humidity effect on the vapor pressure gradient, and it's defined as the ratio of water content in the air relative to the maximum content that air can hold at a given temperature. Okay. So, for example, at 100% relative humidity, we're abbreviating that RH here, and 20 degrees Celsius, the air has a vapor pressure of 0.002 megapascals, which is equivalent to a water potential of 0 megapascals, such as we see, as we've talked about, say, in a beaker of water. or in saturated soils. And so where is this sort of relevant? Well, this would occur in the substomatal space where the relative humidity is almost always in the leaf at 100% relative humidity. Now we're going to compare this to, say, an atmosphere of 50% relative humidity and 20 degrees Celsius. Okay, and here you're going to see a vapor pressure equal to 0.001 megapascals. So a bit drier air has a bit lower vapor pressure, and that's going to equal more or less a water potential of negative 93.5 megapascals. So there's a big water potential gradient here and a vapor pressure gradient that you see here from 0.002 to 0.001 megapascals. So that means water would flow, or water vapor would diffuse out of the leaf into the atmosphere. Now that's given at the same temperature. Let's look at the effect of temperature next. And remember, temperature, or let's say as we increase temperature, increases in temperature will increase the energy of water molecules so that more water can enter the vapor state. So temperature is certainly going to have an effect on evaporation. So we'll start with an example here where we're looking at air temperature equals 20 degrees Celsius at 50% relative humidity, and we have to use a lower relative humidity because at 100% relative humidity it doesn't matter what the temperature is, they always have a water potential of 0. So we'll drop it down to 50% relative humidity for comparing this. And again, whoops, we've already seen how that's going to create a vapor pressure of 0.001 megapascals, and that's again going to have that water potential of negative 93.5, just like we wrote up here for cutting the relative humidity in half. Now let's say we add 20 degrees plus 10 degrees, which is 30, at 50% relative humidity. And that's going to produce a vapor pressure now of 0.002 megapascals. But in this case, the water potential, because of the increasing temperature, is going to, going to drop to 96.7 megapascals. So here you see, again, following that water potential gradient, that the higher the temperature, the lower the water potential. So that means this air is no longer saturated and can continue to accept or be continued to concentrate more and more water vapor into that atmosphere. All right, then the third climatic factor that we want to pay attention to here is wind. And when we have greater wind speed, as we'll see in the next diagram, that is going to create a thinner boundary layer. Thinner boundary layer means lower boundary layer resistance, less resistance for the water vapor to diffuse out of the leaf into the atmosphere. And a lower boundary layer resistance means a higher vapor pressure gradient, or we were symbolizing it like this. So in other words, the difference between the vapor pressure inside the leaf in the substomatal air spaces compared to the atmosphere. Okay. Let's see, so it creates a steeper vapor pressure gradient, and that's going to do what to transpiration rates? It's going to increase the transpiration rates. So then you could just apply the opposite. Lower the wind speed, or the stiller the air, the thicker the boundary layer, and therefore the larger the boundary layer resistance. It's more resistance for water vapor to pass out into the atmosphere. So if we have a higher boundary layer resistance, then there is a less steep vapor pressure gradient, which means that transpiration rates decrease. Okay. Now the diagram that we're looking at here does highlight the effect of wind, so that down here where stomata aren't very open, there is, when stomata open, then as long as the air is still, then they lose very little water because that boundary layer resistance is high. But at, say, the same opening, if we've got a lot of moving air up here, then there's a greater degree of transpirational water loss because the boundary layer resistance is lower. This is a thinner boundary layer because the air is pushing that layer of dead air. That wind is pushing that layer of dead air surrounding the surface of the leaf away from the leaf. And again, that's going to increase the vapor pressure gradient, which is going to lead to higher transpiration rates. Now, so this highlights all the various climatic effects on the boundary layer and therefore the boundary layer resistance and how that would impact transpiration here. But let's remember stomata do ultimately control how much water leaves the plant. So stomatal conductance is the rate at which water is actually moving through the stomata versus when they're open, and versus stomatal resistance is how closed the stomata are. And stomatal resistance will actually increase when the vapor pressure gradient goes up so that the plant doesn't lose too much water. Okay. So let's say if the vapor pressure gradient increases between inside and outside the leaf, where that's going to drive higher transpiration rates, then we're actually going to see the stomata respond by closing down and increasing the stomatal resistance. Okay, so that's how we want to, so we think about the effects of environmental or climatic factors before stomata respond, but then we have to, after that fact, consider how stomata respond after to that vapor pressure gradient. So now we're looking at various structural adaptations that allow an increase in boundary layer resistance, and if that boundary layer resistance is high enough, that's going to reduce the vapor pressure gradient and then perhaps allow the stomatal conductance to increase and allow, in other words, the stomata to remain open. So one example is this drought deciduous Acatillo, where it drops its leaves during low water availability. It also has these smaller leaves here. Another adaptation is these sunken stomata, where they are found in crypts, as you can see here, and that's going to elevate the vapor pressure, VP here, and therefore reduce the diffusion of water vapor. Hairs or trichomes reduce the movement of air across the surface of leaf, thereby increasing boundary layer resistance once again. And then these are situations here where the reduced leaves into spines aren't going to have any transpiring surfaces, or reflecting solar radiation coming in is going to help cool the plant and therefore help reduce water loss. The other aspects of structural modifications or structure and how it affects vapor pressure gradient or boundary layer resistance is the leaf size and the leaf shape. So the larger the leaves have higher boundary layer resistance,
Whereas a leaf that is shaped like this entire leaf will have higher boundary layer resistance than a divided leaf where air can flow across the surface.